Okay, hello everyone. My name is Maria Eduarda Andrade, and I'll be speaking about our paper on model pruning and depth completion, CNNs for forestry robotics with simulated annealing. So, as everyone mentioned, why do we work in forestry robotics? Wildfires are greatly affecting our lives, especially in the Portuguese life. During the last 30 years alone, 40% of all wildfires in the Mediterranean have occurred in Portuguese forests. So what can we do to prevent that is forest maintenance. One of the ways we do that is, as engineers is doing, is mulching inflammable materials during low season, for example. However, there is a lack of manpower to do forest maintenance year-round. Therefore, we need some kind of fully or semi-autonomous robotic solution to overcome that. Although we are still in development stages due to limited perception capabilities. So our motivation, as I said, was to do forest maintenance, which in our case is to identify flammable material. It is crucial that we need some tools and sensors. One of the ones we use is the LiDAR, which allows us for a 3D panoramic view. However, as you can see in the image, it does have some sparse image in comparison to RGB. It only has half the points in the RGB image, and even so, each line is scarcer than the actual RGB. So one way to do this is to use depth completion, which is an area that has gotten significant knowledge in the urban environment, especially for autonomous cars, but barely any for forestry robotics. Besides that, most of the methods today that are top of the line are multi-sensor approaches that uses RGB and depth image. However, both it is a computationally costly method, and we need to be able to overcome that. One of the ways we decided is to try some model pruning, which is a technique which basically compresses a very dense model to a much lighter by removing unwanted or unnecessary parameters from the original convoluted neural network. However, I have not seen much or any research in completion specifically and forestry application. So what was our goal? Was basically, our first goal is to use multi-sensor registration and fusion of camera image with little depth completion to create a dense depth image that will be done by using different depth completion CNN techniques. Now, the main focus of this paper is to present a proof of concept study to showcase the performance of model pruning in depth completion CNN's models. Pruning allows us to achieve real-time operations, and this paper assesses its impact on depth completion performance using 2 different CNNs and 3 distinct data sets. Basically, model pruning basically lowers the amount of weights and connections in the neural network. As you can see in the image, they're deemed redundant. So the first neural network we used in this paper is called ENET, and it was developed by Hugh and published last year at ICRA. It is a very robust and highly layered neural network, and it achieved state-of-the-art results from the KD benchmark last year with a root mean square error of 741.3 millimeters. The way it works is it breaks down into 2 branches. The color dominant uses an RGB and depth sparse input and outputs a completed depth map. Then this depth map is used as input with the previous sparse step to a depth dominant branch to achieve a final output of a depth completed map. Because of these 2 branches, it is a highly layered neural network with 120 convolutional layers, which means it has a very high inference time. For comparison, it uses 350 gigaflops, which is floating operations. I'll explain it a little more later. In comparison, ResNet 50, which is a highly used backbone in semantic segmentation, only uses 7 gigaflops. So it is 50 times larger than ResNet. The second approach I'm going to talk about today is called Multi-Scale Guided Cascade Hourglass Network, or MSG-CHN. It is a much lighter network in comparison to the previous ENET. It only has 45 convolutional layers, and it was published in 2020. At the time, it achieved state-of-the-art also at the KD benchmark with an RMSE of 762.2 millimeters. In the case it doesn't use 2 branches, it just lowers the resolution and scale by half 3 times of each input and then join them together to find the final output. It still has a very high inference time because of the 31 gigaflops. As I said, in comparison with ResNet, which has 7 gigaflops, it is also almost 5 times larger than ResNet. Now I'm going to discuss the data sets that we used. The first one is the Kitty. Kitty, as I mentioned, is a highly used benchmark for depth completion, and it is used for autonomous cars perspective in an urban environment. It comprises of 720p RGB image or HD image, and for the depth map, it uses a LiDAR. The reason why we chose this is because both neural networks were trained in the data set, and therefore it will be a great basis of comparison for both models to see how it will behave with a model pruning. The SimForest was the one mentioned just before from Professor Peixoto, which is a synthetic data set in a forestry environment. It uses 480p RGB image at input, and we also have a full ground truth depth map. For the input, we created a mass depth map simulating a 16-line LiDAR. It is also great data to test because since it is synthetic, we don't know how the models usually behave with this data set, and model pruning should behave differently than for Kitty, for example, which is an urban environment and uses real images. And lastly, we use UA Soil Garden, which is a new data set with high resolution recorded in a garden at University of Alicante. It has 2K RGB images, and the depth map uses a Z camera stereo dense map. For the input, we use the same mask as for the SimForest. So all 3 data sets comprises of information that would benefit for the model pruning, so we identify which sparsity would be the best. In this slide, I'm just showing some examples of each of the data sets and using one of the neural networks, in this case, MSG-CHN. The top is the input for each one of them. As you can see, Kitty is very urban. Even the ground truth is not as dense as the other ones. While the SimForest is highly well made, it's still very synthetic, but however, you still have a very dense ground truth, which is very interesting for our MSC evaluation. The mass for the input is definitely in Kit is denser than SimForest and USO. However, the ground truth for SimForest is highly detailed. So the main focus of this paper is the model pruning. So what did we do? We used a simulated annealing model pruner, which was developed by you 3 years ago, because meta heuristics have shown great results finding optimal solutions for a general task. It uses a general simulated meta heuristic approach, which basically it sets an initial temperature, final temperature, cool down rate, and generate a solution to see if the evaluation metrics are met. If they are, you update the model. If not, you see if it accepts with a specific probability. If it doesn't, you just adjust the temperature until a final temperature is reached. That is the basis of simulated annealing. It is supposed to be stochastic and to find the optimal solution based for a general problem. In the case of model pruning, we use this in an initial CNN model that was trained with specific hyperparameters for each one of the 2 neural networks. We set the initial temperature as 20 degrees, final at 100, cool down rate of 0.9, and the pruning rate will change for each sparsity. For the solution, it adopts a guided search based on prior experience, which removes more weights in layers with the most parameters, as it affects the overall accuracy the least. Each solution creates a new perturbation, which is a change of weight pruning rates. After generating a new solution, we calculate the RMSE in the validation set and we get the evaluation criteria. If it is higher than the previous model, you update the model and adjust the temperature. If not, it can still replace it according to a probability acceptance function, which depends on the temperature and the difference of the evaluation function for the 2 competing solutions to avoid getting trapped in the local optima. If the probability and the RMSE are not accepted, maintain the model and adjust the temperature. When it reaches the final temperature, we will save the optimal model for that specific sparsity. So I've been talking about these 2 metrics and I'll explain them further now. The floating operations or flops is a GPU performance metric. So basically just tell us how many operations are going to be needed for that task. It is ideal for
Marta, we've lost you.
Sorry?
We heard you pretty well most of that time, but now you've gone so quiet we can't hear you.
Oh, really? Is it better now?
It was acting a little bit flaky at times.
Okay.
I thought it was because you were looking up.
No, I really don't. Is it better now? Because I haven't done anything. I haven't moved, so I'm not sure what will be the issue.
Now we hear you clearly again.
Internet.
We must have an internet issue, but we have you back, so we'll please resume. Sorry to interrupt you, but I didn't
Oh,
want
no.
you talking and not be heard.
Okay. So yeah, so the floating points operations is the GPU performance metric. So basically just tells us how many operations are going to be needed for that task. It is ideal for us because we have different hardware scenarios. For example, in my laptop right now, I have a RTX 3070, while the one at the Engineering Ranger uses a 2060 Super. So that way we can measure the exact operations that we need instead of the inference time, for example, that just analyzes based on the GPUs we have at hand. The second metric is very common metric for data completion accuracy, which is called root mean square error, or RMSE. It analyzes similarity between the ground truth and the prediction. This is the formula for the RMSE here. In our case, specifically, we're using what we're calling delta RMSE. So we have the original RMSE values for each data set with no compression or model pruning, and then we compare with each level of sparsity. For example, at 10% sparsity, we compare to the original model. Let's say the original model has 100 RMSE. The new model at 10% sparsity has 120. That will mean a 20% increase in the delta RMSE. So what was our basic experiment? We used the two neural networks I mentioned, ENET and MSG-CHN. Then we trained and tested into 3 data sets, the USO, Kitty, and SimForest. All of the models were pre-trained from the original model. I reused the same hyperparameters and number of epochs to try and guarantee reliability and experiment reproducibility. We evaluated the RMSE and the flops at 5% sparsity increments from 10 to 75. So we have 0 as the original and then 10, 15 up to 75%. For the ENET, what we found is that at 0.1 sparsity, the behavior is very inconsistent. So USO and Kitty improved a little bit the results, while SimForest decreased significantly. The RMSE had decreased by 225%. That could be just because of the resulting perturbation is highly unstable and it removes actual necessary parameters in foreseeable ways. However, after that, all of them stabilize up to 75%. You can see that it barely changes any of the RMSE values and stays steady at almost at 0%. Therefore, we can say that the ENET model highly benefits from training redundant parameters, and we can easily put at 75% sparsity as our goal, which lowers flop by half and still maintain the same accuracy. For the MSG, it behaves inconsistently at 0.1 sparsity. USO and Kitty improved results, while again the synthetic decreased by 113%. Since it's a lighter weight neural network, increasing the sparsity actually changes a lot. So the more we increase the sparsity, we can see that the results change depending on the data set. The Kitty stays almost the same, while the USO improves at 75%. Unfortunately, for the synthetic, you can see that the error increases marginally from 65 to 75%, increased by 3 times. So it is still possible to optimize MSG by 60%, although it's not 70% as ENET as expected, since it's already a much lighter weight neural network. So at 0.6 sparsity, we can decrease flop by 70% while increasing accuracy, decreasing accuracy by up to 9.6% at the SimForest. So to conclude today, our paper has shown that the model pruning was effective in optimizing inference for real-time applications. The simulator level model compression has shown to improve the model efficiency without decreasing the error significantly in both neural networks, and can be used as 75% sparsity for ENET, which reduces flops by 50% with almost no accuracy change, while the MSG at 60% sparsity has decreased flops by 71% with a maximum 9.6 decrease in accuracy, which happened at the synthetic data set. So what we like to do in the future, we would like to be able to test and compare other compression techniques with the one we utilize today. To simulate an annealing, we would also like to be able to introduce data augmentation and fine-tuning after pruning to see how well it will improve the results, since the changing weights could create these random behaviors. And fine-tuning could be able to improve or stabilize this. Thank you so much.
Yes, so are there any questions for Maria?
I see Paulo Coimbra is asking online.
Okay.
At least his hand was up.
I think he can unmute himself at this point.
Yes, please.
Well, actually, I was just cheering up. I was not about to ask any question.
Okay. Well,
Sorry.
Okay. Any questions then? If not, I have one. You can hear me well, Maria?
Yes.
Okay, one of the things that surprises me is that a lot of people are tackling the same problem the same way. You all talk about semantic segmentation, image segmentation. And in the end, what we have is not really images. It's more like a sequence of images or videos or whatever. Well, my point being, everyone is worried about spatial stuff. No one seems to care much about time. And I know that there are plenty of fluctuations in sensors over time, in which in one frame you have a very good segmentation result, in the frame immediately after you don't. This happens quite a lot, especially if you consider depth, because you have a lot of noise there. And my question is, why are we not considering time as well?
You mean my results?
Yeah. So is there a plan to at some point consider spatial temporal information instead of just spatial information? That's well, my question.
Well, in this case, we are considering time. It's just that it is much harder to be able to compare time when I was using different machines to test these neural networks. Sometimes I would have access to a better computer. So it was very hard to be able to test in the same condition every time. The best way to test that was to use floating operations, because that's consistent. If a computer reduces by half the amount of floating operations, that should reduce time by half, or at least by a lot. So it is definitely something we can consider when we have a very stable and specific setting. However, it is much better to consider operations, floating operations, as a general compression or optimization evaluation metric.
Maria, sorry. Thank you for the answer. But I was not talking about the time that it takes to compute the method or whatever. I was more concerned about the fact that people are ignoring the information that we have over time. So it is obvious that a given frame that we're trying to understand, that we're trying to semantically segment, as a very large likelihood of relationship with the frame immediately before. So my question is, why are we not considering the information over time to try to improve our results? I don't know if I'm making myself clear now.
Okay, so you're using temporal information as one of the inputs for the system.
Exactly. How to code this information, basically. Yes.
Well, I would definitely say it's not the scope of this project. In my opinion, I would say that it is possible. One of the ways is just using tracking instead of using detection at every frame, as we've been doing. It's just lower and use tracking instead, because tracking is much lighter. We can use a simple common filter and things like that to be able to continue that. That's the whole, while the next step of the mapping that we would like to do in the project will be to use tracking information as also as detection. Regarding temporal information for the neural networks, I haven't really studied that, so I can't give a very specific opinion on it.
Okay, thank you. Are there any other questions?
We have a question in chat.
Okay.
Go ahead.
You can unmute yourselves now.
Here we come.
Hello, can you hear me?
Yep.
Yeah, well, I tried to unmute, but then somebody muted me, I think. So I wasn't about to ask a question. I was about to help Duda in her answer because I'm one of the co-authors. I was just going to say that, yes, we will explore this in the future. But of course, there's a lot of leeway in terms of things that we have to explore in terms of semantic segmentation and all of these perceptual and image analysis issues. So yeah, we're still early days and we'll get there. Eventually, one of the things that we might even also explore is actually the sequence of images itself and how they all relate in time. But anyway, yeah, it's a bit out of scope for Duda's work in this particular case.
Okay, thank you, Jean-Philippe. Any other questions? Okay, so before we leave for the posters, I think someone had a question before for Vincent Condin, and we were unable to have her speaking back then. I don't know if the person is available or not at the moment.
No.
There's someone in the
Well,
room.
thank you, Maria, for your presentation.